All right. Start that around the class, please. Michael Dubach is not here. Carter Dewberry, not here. Derek Heineman. Tyler Koshaway. Anthony Lee. Chris Macklin. There you go. Deja McClellan. Joey Najira. Joey Najira here. No. Jory Owens. What's your name? Name?
Tyler.
Tyler Koshaway, right here. Here you go. Lauren Pendergrass. Val Peterson. Stephen Turner. Megan Walker. And Zach Woodard. All right. Any of you have not gotten a copy of the bonus exam? Come with me after class to my office and I'll give you a copy. The sign-in sheet's going around. Make sure you sign it. Now, there's something else I was going to say. And if I remember it, I'll say it. Does anyone have any questions from the homework? Anyone have homework ready to turn in? No and no. Yes? Excellent. Thank you.
Probably about 88.
88?
Yeah. Take the half paper later, I still couldn't figure it out.
All right. $88. Weight of 800 pounds is suspended from two cables as shown in the figure. What are the tensions in the two cables? Cable 1, cable 2. There's your box. The box weighs 800 pounds. So we draw us a vector diagram. The tension in this cable is T1, pulling in that direction. The tension in this cable is T2, pulling in that direction. And the force of the box is the weight at an angle of 270 degrees. What's the angle of T1, the T1 and T2? This is 50. And this one is what? 35? Okay. So how do we find this one? 50 plus 35 plus that one has to equal 180, right? So we've got 180 minus 50 minus 35 equals, somebody with a calculator, help me with the arithmetic. I got 195. Everybody else get 95? Okay. If that is 95 degrees, how do we find this angle and that angle? Yeah, no, you can't really because they're not equal. No. No, but if this box top is parallel to this line here, then this angle has to equal this angle has to equal that angle. Does everyone see how that works? If you have two parallel lines, then this angle and this angle have to be the same. This angle and that angle have to be the same. Okay? All right. So we've got T1 at 50 degrees to the horizontal and T2 at 35 degrees. So now we draw those three vectors. Now, next step we're going to do is we're going to write these in rectangular coordinates. Because, Michael, here, make sure you sign in the sign-in sheet. Why are we going to convert? Why do we need to decompose these into their coordinate components? They're rectangular components. This is very germane to the rest of the lecture today because we need to add them. We need to write equations where we're adding vectors so they sum to 0. And in order to add vectors, we need them in rectangular coordinates. So the weight of the box, our first vector, is how much of it is horizontal? Jimmy? How much of the 800-pound vector is horizontal? And how much is vertical?
All vertical?
It's all vertical. So it has 0 times the I vector, the unit vector I, and it's negative in, it's at 270 degrees. So Let's step through this one step at a time. We're decomposing this, and I don't want to just do it by eye. I want y'all to see what's happening. What is it in rectangular coordinates? It's its magnitude, 800, times the cosine of its angle, times the unit vector I, plus 800 times the sine of its angle, times the unit vector j. Right? You'll recall in the Cartesian coordinate plane, the rectangular coordinates, I is the unit vector along the x-axis, and j is the unit vector along the y-axis. So any scalar that you multiply either of those vectors by will simply become a vector of that magnitude. So we convert this, the weight of the box, into its rectangular coordinates or Cartesian coordinate form. Cosine of 270 degrees is, you use your calculator if you like, but it's 0. So that goes to 0, and we get 0 times I. Now we add 800 times the sine of 270 times the unit vector j. What is the sine of 270? Negative 1. So it is minus 800 pounds times the unit vector j. That's this vector. Now we've got T1 times cosine 50 magnitude of T1 times the cosine of 50 degrees I plus the magnitude of T1 times the sine of 50 degrees j. Now here's where we need to be careful. Remember, in order for this to work, these all need to be in standard position. Does everyone remember what standard position means? It means the angle that it's pointing in has to begin as the positive x-axis and rotate around to here. So this is not T2 times cosine of 35. It's this angle here, which is 180 minus 35, which is 145. Somebody confirm that. Did you actually punch in the numbers, or did you just say he's right? Okay. All right, so we now have the vector T2, which is written as the magnitude of T2 times the cosine of 145 degrees times the unit vector I plus the magnitude of T2 times the sine of 145 degrees times the unit vector j. And those are our three vectors that are involved. Looking at this box, we know that it is hanging stationary. It is not moving. If you have taken fundamental physics, you know that force equals mass times acceleration, and if it's not moving, then its velocity is 0, its acceleration is 0. So that means that the forces in the vertical direction have to all sum to 0, and the forces in the horizontal direction have to all sum to 0. Quick quiz here. How many unknown values are we trying to solve for? We are looking for two unknown values, T1 and T2. That means we have to have two independent equations. Have we covered that? Anytime you're solving for unknowns, you have to have two independent equations. And what do I mean by independent? That means they have to be, you cannot be able to derive one of the equations from the other. Okay? How many of you in here are studying electronics technology, electricity? Anybody? Yeah, y'all are? What are some of the other fields y'all are studying? Construction management? Okay, well, stick with the electrical thing. If we're talking in electronics, there's something called Ohm's law. It says the current in a circuit is equal to the voltage divided by the resistance. Everybody, have y'all at least seen this? Okay, well, I can rewrite that same equation as resistance is equal to voltage divided by current. Or I can rewrite it as voltage is equal to current times resistance. Now I have three equations and three unknowns. Can I solve for any one of them? Cannot, because it's not three equations. It's one equation rearranged three different ways. They're not three independent equations, so you can't solve for three unknowns. We're looking to solve for two unknowns. We have to have at least two independent equations. And that's what we're going to construct now. We've got the horizontal components and we've got the vertical components. And they have to add to zero independently. That means 0 plus T1 times cosine of 50 degrees. That's the magnitude of T1 times the cosine of 50 degrees, plus the magnitude of T2 times the cosine of 145 degrees, must be equal to 0. We'd also know that the vertical have to sum to 0. That means minus 800 pounds plus the magnitude of T1 times the sine of 50 degrees didn't start far enough over. Minus 800 plus the magnitude of T1 times the sine of 50 degrees plus the magnitude of T2 times the sine of 145 degrees must also equal 0. I can rewrite that one straight away as T1 sine 50 plus T2 sine 145 must equal 800 plus 800 pounds. And this one I can rewrite as T1 times cosine 50 must equal minus the magnitude of T2 times the cosine of 145 degrees. Is everyone with me so far? Well, I can immediately write T1 into the magnitude of T1 in terms of T2 as the magnitude of T1 is equal to the magnitude of T2 times the cosine of 145 degrees divided by the cosine of 50 degrees. I can now take this value of T1 and plug it in here and write the magnitude of T2 times cosine 145 divided by cosine of 50 times the sine of 50 plus the magnitude of T2 times the sine of 145 is equal to 800. Now, do you notice that the only unknown here is T2? I can factor out T2. Cosine of 1 times the cosine of 145. What's sine divided by cosine? Come on, people, this is a trig class. Sine divided by cosine is the tangent of 50. So I've got cosine 145 times tangent of 50 plus the sine of 145 is all equal to 800. Somebody with a calculator, do that calculation. 145 times cosine times 50 tangent plus the sine of 145 equals, don't clear your register, but somebody tell me what it equals. 0.40265 ... So don't round anything off because that just introduces rounding error. But that times the magnitude of T2 is equal to 800 pounds. So if we take 800 and divide it by that number, now once you've already got the number in, just take the reciprocal of it and multiply by 800. And you end up with 800 with T2, the magnitude of T2 is equal to minus 1987 pounds. Is that what everyone else gets? And I'm going to cheat and look at my answer keys that I've already worked out the problems. See if that's what I got too. And that is not what I got. $800. Did I punch these numbers in wrong? Yeah. That's the same numbers. Everybody else, punch the numbers, see what you come up with. Did I lose a sign somewhere? That's what I'm looking for. What? Where? Is I sure did. There it went, right there, people. That means this should be a negative. Which puts a negative here. That's exactly what I did. Somebody redo the calculation where this cosine 145 times tangent 50 is negative. And when you divide it into 800 pounds, .2. Yep. There we go. So now, now that we know T2, we can immediately solve for T1. By plugging in 516.2 here, multiply by the cosine of 145, and then divide by the cosine of 50. And we get, no, don't lose your sign again. Negative T2 times the cosine of 145 is a negative. So that's going to make it a positive.
Can't imagine why I had a problem with it.
Yep, not all of the problems can be, dirt simple. Sometimes you're going to have to think your way through them. So what did you come up with for T2? There you go. If you noticed on the problem right before this, the one that you could just look up the answer in the back of the book, the weight of the box was 1,000 pounds, wasn't it? Yeah. And it turned out that the tension in one of the cables was the full 1,000 pounds plus additional tension in the other cable. That was just a curious, that kind of surprises a lot of people when they see that, to realize that the tensions can add up to more than the weight of the box. But they do here. You got 500 plus 600 is what? 1,100 pounds? If tension, just to hold up an 800-pound box. Now, any more questions from the homework? Okay. Well, I've got a whole class again. Michael DeBach. There you go. Carter Dewberry. Derek Heineman. Derek Heineman. There you go. Anthony Lee. One for you. Deja's not here. Turning in homework. Joey Najira. Lauren Pendergrass. Val Peterson. Megan Walker. Zach Woodard. All right. And anyone who came in late, I'll remind you again that you can come with me after class. And if you haven't already gotten a makeup exam, you can come with me after class to pick one up in my office. They are due on Thursday in class. If you bring it back Thursday after class, it's too late. Do not miss the opportunity to get rid of one of those bad test grades. Okay. Last time we looked at vectors and some of their properties. Somebody tell me the difference between a vector and a scalar. Just say them on top of my book there, it's fine. What's the difference between a vector and a scalar? Yes. A scalar scales a vector. A scalar is just a number, a magnitude, without any associated direction. A vector is a number, a magnitude, that is also associated with a specific direction. It points in a particular direction. So a vector has both magnitude and direction. A scalar has only magnitude. And one of the properties we saw is that if you multiply a vector times a scalar, you just scale the vector. Make it longer, make it shorter, but you change its magnitude. That's how we came up with the unit vector. And then we made special unit vectors, I and j, that associate with the axes of the Cartesian coordinate plane. So we can then conveniently decompose vectors into rectangular form, into Cartesian components that are mutually orthogonal. They're at 90 degrees to each other. And because of the way vectors add and subtract, in order to do that, we put them into rectangular form, and then we can just add the horizontal components, add the vertical components. We don't have to go through all the graphing out vectors and trying to make precise measurements. We can just algebraically solve for the sum or difference of vectors. But what happens if you want to multiply two vectors together? Now, obviously, if you multiply a vector times a scalar, that's easy. Just changes the length of the vector. But what if you multiply two vectors together? What does that mean? What does that picture look like? First question you got to ask is the product of two vectors another vector? Or is the product of two vectors a scalar? And the answer is, it depends on how you multiply them. You can multiply two vectors together in such a way that the product of the two vectors is itself a third vector. And that's what we're going to learn about on Thursday. That's called the cross product. Today we're going to learn about how you multiply two vectors together to produce a scalar. And this is called the dot product. V dot W is how you write the dot product of the vectors V and W. So, first let's just take a moment and look at exactly what this means. If V is V sub x I plus V sub y j, and W is W sub x I plus W sub y j, these are the two vectors V and W, then V dot W is defined as V sub x times W sub x plus V sub y times W sub y. You'll notice that at nowhere in this sum are there any unit vectors. It's just the product of magnitudes. And so the net result, this sum, is a scalar, not a vector. That is the dot product. That's as hard as it gets. Product, it's the sum of the product of the parallel components. Product of the x component magnitudes plus the product of the y component magnitudes is the dot product. It's just a big scalar number. You can punch it right into your calculator. Because the dot product produces a scalar quantity, you will often find it referred to as the scalar product of two vectors. So, if you advance into other classes and you hear one professor talking about a dot product and another one talking about a scalar product, or if you hear one instructor talking about dot products and scalar products, you know already they're both the same thing. They're just two different names for the same thing. This is what they're talking about. Now let's look at some of the properties of the dot product. Because we are also going to learn that there are some things you can do with the dot product that are awfully convenient when you start trying to analyze things. Like determine the angle between two vectors. Or well, we'll get to that. But first, let's look at some of the products, some of the properties. The first property we're going to look at is the commutative property. In this case, V dot W is equal to W dot V. Doesn't matter which order you put them in. The product will be the same. Let's look at it. V dot W is Well, we've already written it out. Vx Wx plus Vy Wy. But that's just scalar multiplication, so it doesn't matter which order you put them in. You can add them or subtract them in any order. So that's equal to Wx times Vx plus Wy times Vy, which is W dot V. Dot products is commutative. You can put them, it doesn't matter which order you multiply them in. They are also distributive. We're going to need a third vector, so we'll call it U equals Uxi plus Uyj. Now, U dotted with the sum of V plus W is equal to U dot V plus U dot W. Let's take this. V plus W is Vx plus Wx I plus Vy plus Wyj. And if that's dotted with U, then we get Ux dot times Vx plus Wx plus U sub y times Vy plus Wy. What if we analyze this side? That side is Ux Vx plus Uy Vy plus Ux, well, I'm running out of room, aren't I? Wx plus Uy Wy. What do we have over here? Ux dx plus Ux Wx plus Uy Vy plus Uy Wy. We get the same sum on both sides. Ux dx plus Ux Wx plus Uy Vy plus Uy Wy. Remembering that once you start adding these together, it all becomes scalar. I'll reclaim some board space there. Now let's look at V dot V. They tell us that this is the magnitude of V squared. Well, what is V dot V? It's Vx plus, try to write that a little more legibly. V sub x times v sub x plus v sub y times v sub y. That's v sub x squared plus v sub y squared. What is that? V sub x and v sub y, these are your product, and this is your vector. Here's v sub y, here's v sub x. What's the sum of the two? This vector here, which is also this vector here. Or at least this is the magnitude of that vector. So this squared is equal to this squared plus this squared. And there's our friend the zero vector again. 0 dot v is 0. Does anybody have any questions yet? No? All right, well. Then let's look at how we can use the dot product of two vectors to determine the angle between them. Let's start with two vectors. They label them what, U and V? Okay. U and V. What would the vector U minus V look like? Here's the vector U. What's the vector minus V look like? Come on, this was last lecture, just last Thursday. You haven't had more than 2 nights of hard drinking since then. So, it's the same vector but pointing in the opposite direction. So, minus V looks like this. Say what? There you go. He's either really brilliant or he watched the video on Canvas. I don't know. But it must just be brilliant. So this is minus V. That means that U minus V would be, add V here and you get, boom, there's U minus V, which is this vector. Now that we've got that, and here is our unknown angle that we want to know, the angle subtended between the two vectors. So somebody else impressed me with your retention of the law of cosines. We're going to, for the moment, just to keep things from getting too complicated, we're going to change that U minus V equals, we're going to define that as a new vector W. So now, somebody regale me with your recollection of the law of cosines. There you go. W squared equals magnitude of u squared plus the magnitude of v squared minus two times the magnitude of u times the magnitude of v times the cosine of theta. All right? No, it's squared. This squared equals this squared plus this squared minus 2 times. If we were solving for the magnitude of w, then we would take the square root of both sides. All right? But there is a little rub in the ointment here. W is actually u minus v squared. What do we know about the property? This is just u minus v dotted with u minus v. And that is the magnitude of u minus v squared. A vector dotted to itself is the magnitude of that vector squared. Property 4 on page 358 if you want to go back and look at it. Well, there's a couple of ways we can address this. Let's start by using it as the, let's use that distributive property. This vector dotted with this sum of vectors is equal to this vector dotted with this vector plus this vector dotted with that vector. Property 3, the distributive property. I'll write it back down again. All right? Since we're using it, I'll go ahead and write that property as well. So, we've already said u minus v is w. So this is u minus v dot u minus u minus v dot v. But that is also a distributive. We can apply the same distributive property here, and we'll end up with u dot u minus u dot v. Doesn't matter which order we put them in. Remember, they're commutative. Minus u dot v minus negative v dot v, which makes it positive. So what we end up with is u dot u minus 2 u dot v plus v dot v, which is u, the magnitude of u squared, minus 2 times the magnitude of u times the magnitude of v plus the magnitude of v squared. Yeah, I'm not going to need to change that. Sorry about that. 2 times u dot v. I'm going to leave it at that. Say again? that is W squared. And that's equal to the magnitude of U squared, this side here, the magnitude of U squared, plus the magnitude of V squared, minus 2 times the magnitude of U times the magnitude of V times the cosine of the angle between them. Well, we can subtract this from both sides and this from both sides, and we end up with minus 2 times U dot V is equal to minus 2 times the magnitude of U times the magnitude of V times the cosine of the angle between them. Divide through by minus 2 over the times the magnitudes, and we end up with U dot V divided by the magnitude of U times the magnitude of V is equal to the cosine of theta. Now, yes, it would be very easy if we knew we could determine this angle, and we could determine that angle, we could decompose these vectors into vertical and horizontal components if we already know those angles. And in Cartesian coordinates form, it's easy to do. You divide the vertical component by the magnitude, by the horizontal magnitude, and that gives you the tangent of the angle, and you can go through and solve all those angles. But if you don't have all of that information, all you have is the two vectors. This becomes a very quick and easy way to determine the angle subtended between them. Does everyone see where this could be? This could be a very beneficial, a very easy way to avoid having to do a whole lot of additional calculations.
You did all that.
Did all of that to get to this. By taking this dot product, dividing it by the product of the magnitudes, that gives you the cosine of the angle. There you go. Example number 2 in the book on page 359. Let's go ahead and work through that one. They give us U and V. U is 4i minus 3j. And V is 2i plus 5j. Just before we start, let's just quickly sketch what these two vectors look like. U is plus 4 minus 3. There is U. V is plus 2 and then plus 5. There's V. What is the angle between them? From that sketch, it might look like they're pretty close to orthogonal, to a right angle. But that's not a calibrated sketch. And actually, even then, it doesn't really look like they're quite perpendicular. So, all right, well, let's start. What is U dot V? Somebody call it out to me. What am I writing? No, I'm writing the dot product, the scalar vector, the dot product. The scalar product? Exactly. So it's 8 minus 15, and that's what? -7. That's our dot product. Now I need the magnitudes of u and v. So now's where we're going to need that square root radical. What's the magnitude of u? Square root of 16 plus 9 is what? Square root of 25. So the magnitude of u is 5. What's the magnitude of v? 4 plus 25. So that's square root of 29, which I don't know. Is that doesn't work out to a nice, even, pretty number, does it? All right. All right, well, what's the cosine of theta then? -7, the u dot v divided by 5 times the square root of 29. And that is approximately equal to, somebody with a calculator, it's approximately equal to minus 0.26. That would give us an actual angle of somebody? 105. Sounds like you lost your negative sign. But that tells us that this is actually a little bit greater than that 90-degree angle that we thought it might be close to. If we didn't use this dot product formula to find the angle between them, what would have been our alternative? If we hadn't studied the dot product yet, how would we find that angle theta? Just think about it for a minute. Somebody, without going through the math, we're not going to do the arithmetic, but what would you have to do to find that angle? Well, we've already got the information here. We've got the numbers. But that's essentially it. Yeah, we would be, at that point, we would have to start taking, well, this angle relative to here and this angle relative to, finding the angle of each vector independently. In other words, the inverse tangent of -3/4 gives us this angle. The inverse tangent of 5/2 gives us this angle. And then we can add those angles together. Or we can just take the dot product and then divide by the magnitudes. You'll notice I just said take the dot product and then divide by the magnitudes. Is that any different than taking the dot product and then dividing by the product of the magnitudes? Just a pop quiz. What do you think? No, it's not going to make a difference. If you divide by the product of two numbers, it's the same as dividing by one number and then dividing by the next number. Division is simply multiplication by the reciprocal. So you can do all of your multiplication in any order. Now, the next thing they introduce in the book, as though it's earth-shattering, is that you can use this property to determine if two vectors are either orthogonal or if they're parallel. How would you do that? What does it mean to say that two vectors are orthogonal? No, they're orthogonal. Actually, they have the slopes, or one is the inverse reciprocal of the slope of the other. If they're orthogonal, they're at 90 degrees. That means theta would be 90 degrees. That means cosine theta would be what? Cosine of 90 degrees is what? Zero. So if vector u and vector v were orthogonal or perpendicular to each other, then you know that u dot v divided by the magnitude of u times the magnitude of v is equal to the cosine of 90 degrees, which is 0. Well, assuming neither vector is the 0 vector, because they like to sneak that little bugger back in every once in a while. If they're both non-zero vectors, then the magnitude cannot be equal to 0. In order for this to equal 0, u dot v has to equal 0. So, if you take the dot product of two vectors and it equals 0, then u and v are perpendicular, or they're orthogonal. Now, what about if they're parallel? How many of you caught it just a minute ago when I was doing this? When I started to write u dot v, and I wrote it as the dot product was equal to the magnitude, the product of the magnitudes. Well, that's not normally the case. It is generally not the case that the dot product of two vectors is equal to the product of the magnitudes. But in the special case, when they are perfectly parallel to one another, when they're parallel, they're either at 0 degrees or 180 degrees relative to each other, then the dot product divided by the product of the magnitudes is equal to the cosine of what? Either 0 or 180. Which means it's either +1 or -1. So plus or minus a sign, if the dot product and the product of the magnitudes are the same magnitude, if they're both, give or take a minus sign, if they're equal, then your two vectors are parallel. You got what, 15 minutes left? Good, because a while ago we were talking about resolving these into horizontal and vertical components. Well, obviously if they're written in this fashion, that's already done. If they're written in Cartesian or rectangular form, they're already broken down into horizontal and vertical components. But that's relative to the x and y axis. What if you wanted to do that relative to some rotated axis or to some other arbitrary vector? We're going to talk about now is the decomposing vectors into orthogonal components relative to an arbitrary line or some other arbitrary vector. When you take one vector and you look at the component of that vector that is parallel to another vector, you know what? Instead of making this horizontal, I want to try to emphasize the point that we're not talking about necessarily the x and y axes. So we're going to take a second vector, w. We've got this vector, v. Now, if we wanted to decompose v into components that are orthogonal to and rotated with that vector in terms of this vector w, then the way we're going to do that is we drop a vertical line, or we drop a perpendicular line from there down to w. And this vector we're going to call v sub w, meaning the component of v that is parallel to the vector w. This is also called the projection of v onto w. Okay, just imagine that you're up there and you shine a bright light directly straight down on w. This component, the projection of v onto w, is where the vector v would cast a shadow if you're shining the light straight down. So it's called the projection of v onto w. Now there's also a vertical component we're going to call v, you know what, I'm just going to call them v1 and v2. So v1 is the projection of v onto w, and v2 is the component of v that is perpendicular to w. Now we can immediately write the vector v is the vector sum of v1 plus v2. Okay, and this, it's important to recognize, this is a vector sum. This is not a scalar sum here anymore. So now if we take the dotted, we dot v with w, we get w dotted with v1 plus v2, which is w dot v1 plus w dot v2. Everybody with me so far? This one is orthogonal. V2 is perpendicular to W, which means this goes to 0. So V dot W is equal to V1 dot W. Now, V1 is just a scaled portion of V, right? So V1 is equal to some scalar alpha times the original vector V. That means we can now write this as alpha times V dot W. No. Back up here. What they're pointing out is this vector V1, it is just a scaled down version of V, but it's also just a scaled down version of W. Right? It points in exactly the same direction as W, but it's going to be shorter. So V1, instead of writing it as a scaled down of V, I'm going to write it as a scaled down version of W. So that means that we now have this scaled down version of W dotted with W. And from our earlier properties, we know that that means this is equal to alpha times the magnitude of W squared. And that's equal to V dot W. So we can find alpha. Now we can solve for alpha is equal to V dot W divided by the magnitude of W squared. Since V1 is equal to alpha times W, here, everybody pay attention, because this is important. I don't want you to lose sight of this, because this is one of those little subtle points that if you let it slip past without noticing, it can come back to confuse you and bite you later. V dot W is a dot product, means it's a scalar. It is not a vector anymore. the magnitude of the vector squared. It's not a vector anymore, it's just a scalar. So this ratio of a scalar divided by a scalar is just a scalar. It is not a vector. This value, this quantity right here, is not a vector. This is just a scalar. This scalar alpha. But V1 that we're looking for, this vector V1, which is the component of the original vector V that is parallel to the vector W, is equal to that scalar times W. So we now have V1 is equal to V dot W divided by the magnitude of W squared times the vector W, scaling that vector. That is the parallel component of V, or the projection of V onto W. How do we now find the vertical component of V? How do we find V2? We make note of the fact that V is equal to V1 plus V2, and we find then that V2 is simply V1 minus V. Sorry, got the signs backwards. Subtract V from both sides. This negative V would be V1 minus V. So V2 is V minus V1, the negative of that. Got to watch those signs. All you got to do is forget one little sign. It just changes everything. That is how you decompose any random vector into orthogonal components relative to any other random vector. And you might notice this scalar alpha looks an awful lot like that whole finding the angle between them dot product. And if you dig deeply enough into the math, you'll find that there is a commonality there, but we don't need to worry about it. Any questions? All right, then come back Thursday and we'll look at taking the product of two vectors that results in a third vector.